So hey guys, today I'll be talking about the data structures for graph. So how we can represent graphs using data structures. So we have typically three data structures, but in this video I would be discussing about the edge list and the adjacency list. Now graphs have typically two components, that is the vertices and the edges. So to start with, we store the vertices and the edges into two containers, and each edge object has references to the vertices it connects. So basically a very simple data structure to start would be an edge list. Edge list is a very simple data structure which is quite easy to implement. It is nothing but it simply stores the vertices and the edges into two unsorted sequences. So for clarity, the number of vertices I'm taking to be n and number of edges I'm taking to be m. So this is typically an edge list. So here is an unsorted sequence of the vertices, and here there is an unsorted sequence of edges. So simply in edge list what we have is that each edge has two pointers pointing to the two of its vertices, right? So there are numerous operations that could be easily done using edge list. For example, given an edge, you have to find it two endpoints, so it can be easily done. So if you want to insert a vertex, that will take order one time. Why? Because these are unsorted sequences. But the inefficiency of the edge list comes when we have to find the adjacent vertices of a given vertex. So for a given vertex, if you want to find your say the adjacent vertex, so you have to traverse through the edge and check for the adjacent vertices. So it will take order m time. Similarly, your remove vertex operation in an edge list will take order m time. So here are the various operations and their time complexity. So we can see that the adjacent vertices take order m time and the remove take order m time. So now we move on to a next important data structure, which is the adjacency matrix. Now what is an adjacency matrix? It is simply a sequence of vertices adjacent to V. So here we typically have an array. So if this is my graph, so I will store my vertices typically again in an unsorted array, and simply I would connect them to a linked list storing my vertices which are adjacent to the given vertex. So for A it would be B, D, B, C, D. For B it would be A and E. For C it would be A, D, E. For D it would be A, C and E. And for E it would be simply my B, C and D. Now if we want to check what is the space this data structure requires is, so first of all this array contains my the n vertices, and I have to maintain a linked list which contains the adjacent vertices to each vertex. So it would acquire my degree V and its summation over all the vertices. Now this is in an earlier result, we can say that the summation of degree of V is twice the number of the edges. So it is n plus 2m, which is order n plus m. Now there are numerous operations that can be done. So the earlier operation which took us order m time, which was to find the adjacent vertices for a graph, here will take order degree of that vertex time complexity, right? Now if you want to So here are various operations. If you want to check whether u or v are adjacent vertices, then it would take order minimum, degree u, and degree v time complexity. Now, one of the most important things that here we need to take off is that here we are not really storing our edge information. So to answer the question of the edge, we can think of an adjacency list and the edge list to get combined. So what we can exactly do is that we can combine these two structures. So for each vertex here, I can combine an adjacency list which has both in and out adjacency list for the simplicity, and this would particularly store my edge information too, like simply telling what the edge is. Now here also the operations like adjacency take order, degree, v time. To check adjacent u and v will take order minimum, degree u, degree v, and removing a vertex also will take order, degree, v time. Thanks.